Okay, this is geometry, section 9.4, symmetry. Objective, students be able to identify the type of symmetry in a figure. You'll need to write that down at the top of your notes. Students will be able to identify the type of symmetry in a figure. Now, essential understanding, some figures appear unchanged after reflection across the line or rotation about a point. Such figures are said to have symmetry. A figure has symmetry if there is an isometry that maps the figure onto itself. Now, the isometries we know about, the isometric transformations we've learned so far, have been reflections and rotations. Today, we're learning about line symmetry, which is reflectional symmetry, and rotational symmetry, and then something called point symmetry. It's where we have rotational symmetry of exactly 180 degrees. Okay, and that's called point symmetry. And that's something that'll be akin to understanding the whether a function is odd when you talk about it next year in Algebra 2, because an odd functions rotate, you can rotate about the origin 180 degrees, and that's point symmetry. So we start that understanding of that with just learning about point symmetry when you rotate 180 degrees. So when we look at this first one, line symmetry, a figure has line symmetry or reflectional symmetry if there is a reflection for which the figure is its own image. So if I have a line I can draw in such a way that if I fold my figure on the line, it can be brought back to itself. That is something called line symmetry. The line of reflection is called the line of symmetry. It divides the figure into congruent halves. A figure has rotational symmetry if there is a rotation of 180 degrees or less for which the figure is its own image. The angle of rotation for rotational symmetry is the smallest angle needed for the figure to rotate onto itself. So in this triangle, if in any regular figure, because all the sides and interior angles are the same, regular polygons, I just divide 360 by the number of sides, and that'll tell me the smallest rotation to bring it back to itself. So 360 divided by 3 is 120, and that's the smallest rotation to bring the figure back to itself. And that rotation is about the center of the polygon. Now, if I talk about point symmetry, it's akin to my rotational symmetry, because if it has rotational symmetry, it's got a good chance to have point symmetry. It's just that that angle of rotation has to go evenly into 180 degrees for it to have point symmetry. So if I'm looking at a figure with 180 degrees rotational symmetry, also has point symmetry. Each segment joining a point in its 180 degree rotation image passes through the center of rotation. A square that is both 90 degrees and 180 degree rotational symmetry also has point symmetry. So if I look at this square and I outline it so you guys can see that I'm going to be rotating another figure. Okay, and I talk about it as rotational symmetry about the center. It comes back to itself after 90, and it comes back to itself after 180, comes back to itself after 270. And again, all figures will come back to themselves after 360. It does not have rotational symmetry if it just has 360. It has to have something less than 180 as a base rotation. In this case, I'm talking about a square, and its rotational symmetry, the basic one, is 360 divided by the number of sides, 4, which is equal to 90. So we're talking 90 degrees, 360 divided by 4, which is equal to 90. Now, as we move on, identifying lines of symmetry. How many lines of symmetry does a regular hexagon have? If I look at that hexagon, and a hexagon is a six-sided figure, okay? So if I pull that down, this is my hexagon. Now, if I draw in lines of symmetry, we're going to draw these in. Not only do I have lines of symmetry coming across the midpoints of the side, okay? And we're going to probably slide that over a little bit. It's got to come over a little bit more. Oops, excuse me. But I also have it coming down from each vertex, going to opposite vertices. So I'm coming down here, across there, I'm coming down here, across there, I'm coming over here, across there, and I'm coming down the center, across there. So I got a lot of people think, oh, there's a ton of them. But let's talk about how many sides I actually have. 1, 2, 3, 4, 5, 6. There's a 6. The rest of them are the other ends of the ones I started counting. Okay? So there are, in a regular polygon, there are just as many lines of symmetry as there are sides or vertices in the polygon. So there are 6 lines of symmetry in this hexagon. Now, draw a rectangle that is not a square. How many lines of symmetry will it have? You guys go ahead and do that while I futz around with my rectangle. Hopefully, you've done that and you were able to see that there are 2 lines of symmetry in that rectangle. Ideally, if I drew those perfectly, that's where those lines of symmetry would exist and would be able to pull those around. Okay, so I'll be able to fold it back upon itself either way. So there are 2 lines of symmetry here. Now, identifying rotational symmetry. Does the figure have rotational symmetry? If so, what is the angle of rotation? Here's the deal. Rotational symmetry happens when I have my rotation come back on itself when it's 180 degrees or less. This went all the way around. So the triangle has no rotational symmetry. It could have line symmetry, but in this case, it doesn't have rotational symmetry. My starfish here has rotational symmetry. It kind of comes back to itself 2, 3, 4, 5 times. So I will have rotational symmetry of 72, 144, 216, 288, because I can rotate all those and come back to itself. But remember, this doesn't have point symmetry because none of these is 180 degrees exactly. Okay. Now, does the figure below have rotational symmetry? If so, what's the angle of rotation? So does this thing have rotational symmetry? We gotta think, does it come back to itself? No way, it kind of does. It comes back to itself. So this has rotational symmetry of 180 degrees. Okay, because I can rotate it and it comes back to itself. And that's how I know. Sliding on, 3-dimensional objects can have various types of symmetry, including reflectional symmetry in a plane or rotational symmetry about a line. Now, reflectional symmetry is a big deal. Reflectional symmetry in a plane means I can take a plane, say I take a mirror, and I can move that along the object up, and as soon as I stop at a certain point, it looks like the object extends down below it. And that's that symmetry that's in there. So if I'm cutting it like this, like think of a block of cheese, okay? Not to make you hungry or anything. But I have not only this horizontal one, but I have a vertical cut on this symmetry. I got a vertical one coming through here, coming across. So I've got that symmetry coming through this way, but I also have one coming the other way. If I cut in here, I've got this one coming in here like this. And I've got a symmetry coming around like this. Okay, and we have that one coming into here right there. So this has actually, if this is a cube, I have 3 planes that I can cut this up into that have reflectional symmetry in a plane. Now my rotational symmetry here, this will spin around on a top and it keeps rotating around and it always comes back to itself no matter how many degrees for my cylinder here. So that's the object can be rotated about a line so that the image matches the pre-image. Now, as far as reflectional symmetry by a plane, there's infinite number of reflectional symmetries vertically. There's only one reflectional symmetry horizontally of this cylinder that we have. So identifying symmetry in a 3-dimensional object. This bowl, if I'm looking down from the top, I have rotational symmetry because as I rotate it around, it's the same with the stripes and everything as it goes around. But as I look at reflectional symmetry, it has that as well. If I'm looking at my water pitcher, it has reflectional symmetry through the handle, but not rotational symmetry. And my lamp will have rotational symmetry, but it won't have reflectional symmetry. Well, it will have reflectional symmetry through the top, coming through the top, excuse me. So if I look on top and cut it down through the axis of the lamp, it'll have reflectional symmetry. Now, these last pieces is your self-quiz. Does the shape have line symmetry? If so, draw on the line of symmetry. Does the shape have rotational symmetry? If so, write down the angles of rotation. So you have 7, 8, 9, 10. Go, give them a try. Oh, by the way, when you're doing this, turn me off so you can try on your own. Okay, so I'm back. So in problem 7, I'm looking at this. I'm going to assume this is a rhombus. Okay, that I know it's not there, but well, I'm looking like I have symmetry there and there. Okay, so I've got line symmetry and I have rotational of 180 degrees. Okay, so line symmetry, rotation 180 degrees, so therefore I have point symmetry. Now in 8, I have line symmetry, that's 1. I have, and by the way, line and reflectional is the same. I don't have rotational symmetry, and I don't have point symmetry because if I don't have rotational symmetry of exactly of 180, I can't have point symmetry. And this next one, it looks like I can spin this 90 degrees each time. So I have 90, 180, and 270. And because I have exactly 180, I have point symmetry. And here I have a hexagon. And by the way, I don't have any line symmetry in this. Here I have a hexagon. We talked about the hexagon. Polygons, regular polygons, have just as many lines of symmetry as there are sides or vertices in the polygon. Okay, so I have 1, 2, 3, 4, 5, 6 lines of symmetry in my polygon. So I've got line symmetry and I got rotational symmetry because it rotates itself because it's 360 divided by the number of sides, 360 divided by 6, 60, 120, 180, 240, and 300. And because it has 180 exactly, it has point symmetry. Okay, give 11, 12, 13, 14 a try. Turn me off and give it a go. Okay, now back on. This is looking like if I spin this around the center, it comes back to itself. So it looks like I have rotational symmetry of 180 degrees and point symmetry because of that rotational of 180 degrees. I do not have line symmetry in this figure. In this next one, boy, you know, this does not look like there's any symmetry at all, just because of the way it's drawn and this side looks shorter than this, okay? In this next one, this triangle looks like it's got no symmetry either because of this side and this side coming through here. And now, one of my favorites, a circle. A circle has an infinite amount of rotational symmetry. So it will have point symmetry because any degree works in a circle. Okay, any rotation, 1 degree, half a degree, 180 exactly, 90, 60, 20, 45, all work, it comes back to itself. Point symmetry, therefore, and line symmetry, its infinite number of lines will be go through that. So that's kind of an interesting deal. So the line, any line passing through the center will work. Rotational, any degree, and point symmetry, because any degree covers 180 exactly. Now y'all go try 15 through 22. Give them a try. Go and see what you know. Remember, turn me off. Now in 15, welcome back, I've got these lines. And this makes it really tough to have exact line symmetry. So I don't have, see how these are curved? I don't have great line symmetry happening for this because of the reflection coming back with the lines. The lines were going a different way, maybe, but right now, no line symmetry. I have rotational because I have 6 equal Shapes or designs. So 360 divided by 6 gives me 60, 120, 180, 240, 300 for my rotations. So I have point symmetry because I have exactly 180. In 16, I have line symmetry. I don't have rotational symmetry. I've got line symmetry there. I just got one. Okay. In 17, I got rotational symmetry of 180 and therefore a point symmetry. In 18, I have line symmetry. I can see that coming across here, coming diagonally. And then I have rotational symmetry of 90 degrees and 180. So I have point symmetry as well. So I should also have point symmetry. I didn't put that in there, point symmetry. Somebody can't spell real well. Let's see if I can get that going. There we go. I just got to pull that out. There. So point symmetry should also be in problem 18 because of the 180 degree rotation. And a rhombus. Now I'm going to put this on if I have a rhombus, okay, no matter what the rhombus would look like, I would have 180 degree rotational symmetry, and I would have line symmetry. And people wondering about that rotational symmetry, and I'll talk about that with 180. I want to make sure that you see that. If this is the same as that, and that, and that, I can bring this back to itself. I know I put it on top of itself, but I can bring it back to itself 180 degrees later. So it should have rotational symmetry of 180. And because it's 180 exactly, and point symmetry. Okay. Now the kite. When I'm looking at a kite, it won't have rotational symmetry. It'll just have a line symmetry, and it'll be one line right down the smack down the middle of it. And if I draw a picture of a kite, it'll look like this, and the tail be a little longer there. And so its long axis is the line of symmetry. A square will have rotational symmetry of 90 and 180, 270, you know, and 4 lines of symmetry, and it'll also have rotational symmetry. Of 90 degrees, 180 degrees, and 270. I can go 270 back to itself. Remember, I'm staying away from 360 because if I don't have multiples of 90, you know, 360 would be already there, but you know, 360 would be there. Symmetry. Somebody's got to, you know, have symmetry. Okay. And then my last one, the parallelogram. There won't be any line symmetry, no line symmetry, but there'll be 180 degree rotational symmetry. So therefore, point symmetry. And I just got to make this bigger. Not sure why it's not letting me make it bigger, but we'll figure that out right now. And we'll squeeze that down so I can put that in. 180 rotational symmetry and point symmetry. Okay. And that's it. That's what we've got. We got the summary. Objective students will be able to identify the type of symmetry in a figure. Write a couple of sentences about something that you've learned today about the learning objective, then rate yourself on a scale of 0 to 4. Hope things are going well, and have yourself a wonderful day. Good luck on the assignment.